We'll start in 1 minute. Today we'll be in section 11.9 again, representations of functions as power series. Remember the test 4 is this Friday. Tomorrow and Wednesday we will go through the test 4 review sheet. So the next example, find a power series representation for g of x equals negative x to the third divided by x to the fifth minus 2. So what we'll do is we'll start with 1 over 2 minus x to the fifth. And then once we find a power series for this, then we'll use that result to find a power series representation for the given function. So in the denominator, since we have 2 minus x to the fifth, we want to write this as 1 over 2 times the quantity 1 minus x to the fifth over 2. And then I'll factor 1/2 out, so we have 1/2 times 1 over 1 minus x to the fifth over 2. And then we can use the geometric series formula to write down the series for 1 over 1 minus x to the fifth over 2. So the first term is 1, and then plus x to the fifth over 2 to the first, plus x to the fifth over 2 to the second, and so on. Okay, so we'll write a couple more iterations. When we raise each of those to a power, we get 1 plus x to the fifth over 2 plus x to the 10th over 4, and so on. X to the 15th over 8. And then if we multiply every term in the series by 2, we get 1/2 plus x to the fifth over 4 plus x to the 10th over 8 plus x to the 15th over 16. Okay, then if we multiply this by -3 over -1, negative x to the third over negative 1 times this series, 1 over 2 minus x to the fifth. And then do the arithmetic, we get the function that we want. We have negative x to the third in the numerator and x to the fifth minus 2 in the denominator. But negative x to the third over negative 1 is just x to the third. So we're going to multiply each of these by x to the third, and we'll get 1/2 x to the third plus x to the 8th over 4 plus x to the 13th over 8 plus x to the 18th over 16, and so on. And if we write it in sigma notation, so each of those exponents has the form 5n plus 3. Okay, so if we start at n equals 0, then the denominator will be 2 to the n plus 1. So let's see if that works. When n is 0, the denominator is 2, and the numerator is x to the third. When n is 1, the denominator is 2 to the second, which is 4, and the numerator is 5 to the 5 times 1 plus 3, which is x to the 8th. So this looks like the power series representation that we want for negative x to the third over x to the fifth minus 2. Yeah, a number of these are sort of tedious, but they're good exercises for you to go through. And the next one, find a function whose power series representation is this sum. The terms are n times x to the n, and n starts at 1 and goes to infinity. Well, we begin with something more basic. This has x to the n in it, so maybe if we look at the power series representation for 1 over 1 minus x. So this is the first one that we looked at. And as long as the absolute value of x is less than 1, 1 over 1 minus x is 1 plus x to the second, and so on. And in sigma notation, well, if we start at n equals 0, then the terms are x to the n. This original power series has a coefficient of n times x to the n. Well, how can we get a series where the coefficients are n? In this series, the coefficients are all 1. Well, if we take the derivative of this function, take the derivative of 1 over 1 minus x, and then on the right-hand side, take the derivatives term by term, Well, let's see what happens. So the derivative of 1 over 1 minus x when we compute the derivative of this, we just get 1 over the quantity 1 minus x squared. And then on the right-hand side, take the derivative term by term, and we end up with 1 plus 2x plus 3x to the second plus 4x to the third, and so on. And this time, let's see, let's start at n equals 1, go to infinity. And then we have n times x to the n minus 1. Let's check a couple of the terms to see if this is the right formula. When n is 1, we have 1 times x to the 0. X to the 0 is 1. So 1 times 1 is 1. When n is 2, we have 2 times x to the 2 minus 1, or 2 times x. And so, yeah, it looks like this is the right formula. Well, this is pretty close to the power series representation we want. What do we have to do next? Instead of an exponent of n minus 1, we want an exponent of n, x to the n. So what would I have to do to n times x to the n minus 1 to get n times x to the n? All I would have to do is multiply it by x, right? Because x times x to the n minus 1 is x to the n. So what we'll do is we'll multiply this function, 1 over 1 minus x squared. We'll multiply both sides of that by x. So we get x over 1 minus x quantity squared. Then on the right-hand side, multiply every term by x. We get x plus 2x to the second plus 3x to the third plus 4x to the fourth, and so on. And in sigma notation, starting at n equals 1, the terms are n times x to the n. So it's pretty obvious, but let's go ahead and check. When n is 1, the first term is 1 times x to the first, or x. When n is 2, we have 2 times x to the second, which matches that. And yeah, so this is the right formula. So let's give this function a name. Let's call it capital f of x. So capital F of x equals x over 1 minus x quantity squared equals this power series. Okay, and in the next part, we're going to use the function that we found up here to evaluate this series. So this series, the terms are n over 3 to the n, as n goes from 1 to infinity. So do you see what we're trying to do? We want to use this function to evaluate this series. So what do we do? So we're going to evaluate capital F of x at a particular number using this function, x over 1 minus x quantity squared. which will tell us what the value of this series is equal to. So here's the question. What is the value of x that I need that will give us this series? Yeah, 1/3. If we replace x with 1/3, we're going to do it in this function as well as in the power series. So f of 1/3 is 1/3 divided by the quantity 1 minus 1/3 to the second. We'll do the arithmetic in a minute, but in the series we also replace x with 1/3, so n times 1/3 to the n. But that's equivalent to a series from n equals 1 to infinity of n over 3 to the n. And then back to evaluating this. So in the denominator, 1 minus 1/3 is 2/3, and then we're going to square 2/3 in the denominator. So we get 1/3 divided by 4/9. This is 1/3 times 9/4, which simplifies to 3/4. Okay, so the value of this infinite series is the number 3/4. As a reminder, the radius of convergence is 1. So the interval of convergence, the absolute value of x, is less than 1. So this series converges when the values of x are between -1 and +1. And when x is 1/3, x 1/3 is in that interval, so we can be certain that this is the value of this series. Okay, let's look at the next page. For this one, use a partial fraction decomposition to find a power series representation for this function, f of x equals 1 divided by 2x squared minus 3x plus 1. The denominator factors pretty nicely. One factor is 2x minus 1, and the other one is x minus 1. We'll write this using the partial fraction decomposition. We'll write it as a over 2x minus 1 plus b over x minus 1. And then with a common denominator, the numerator will become ax minus a plus 2bx minus b over the common denominator, 2x minus 1 times x minus 1. Okay, the numerator, we can focus on the numerator. Ax minus a plus 2bx minus b has to equal 1. So combining like terms, we have ax plus 2bx, if we write it as the quantity a plus 2b times x. That has to equal 0 for all x. And then the constant minus a minus b has to equal 1. So minus a minus b equals 1. Or the coefficient a plus 2b has to be 0. Negative a minus b equals 1. When we add these two equations together, we get b equals 1. And if b equals 1, what's the value of a? What did you get? Okay, if we replace b with 1, we get negative a minus 1 equals 1. Negative a equals 2, so I get a equals negative 2. Is that what you got? Okay, so this function written as a sum of two smaller rational functions. We have negative 2 over 2x minus 1 plus 1 over x minus 1. Okay, so now what? So the goal is to find a partial fraction, use a partial fraction decomposition, which is what we did, to find a power series representation for the rational function. So we'll find power series representations for each of those two rational functions, and then we'll add them together. So let's do one at a time. Negative 2 over 2x minus 1. If we multiply by 1 in the form negative 1 over negative 1, we can write this as positive 2 over 1 minus 2x. And then think of this as 2 times 1 over 1 minus 2x. And then for the 1 over 1 minus 2x part, we can write down a power series representation. So this will be 1 plus 2x to the first plus 2x to the second plus 2x to the third, and so on. So let's write it as 2 times the quantity 1 plus 2x plus 4x to the second plus 8x to the third, and so on. And if we multiply everything by 2, we get 2 plus 4x plus 8x to the second plus 16x to the third. See, the next one would be 32x to the fourth, so on. Okay, so this is this first term, negative 2 over 2x minus 1. Then we'll find a power series representation for 1 over x minus 1. So what do we do in this case? Well, let's multiply by 1 again in the form -1 over -1. So we get -1 over 1 minus x. And then factor the -1 out. So we have -1 times 1 over 1 minus x. And then we write down a power series representation for 1 over 1 minus x. That's just 1 plus x squared, and so on. Okay, so 1 over x minus 1. When we distribute -1 by multiplying, we get -1 minus x squared minus x to the third, and so on. Okay, so now what? We're going to add those two series. So we're going to add this series to this one. So let's do that term by term. But I'll write down that it's after we add those, it's going to be equal to 1 over 2x squared minus 3x plus 1. Okay, so here are the terms from -2 over 2x minus 1. Here are the terms from 1 over x minus 1. Okay, so when we add them, 2 plus -1 is 1. 4x minus x is plus 3x. 8x squared minus x squared is plus 7x squared. 16x to the third plus -x to the third is plus 15x to the fourth. Sorry, 15x to the third. Then the next one, 32x to the fourth plus -x to the fourth is plus 31x to the fourth, and so on. So let's see if we can come up with a sigma notation for this. So the variable parts are pretty easy. X to the 0, x to the first, x to the second, x to the third, and so on. Okay, so I guess we can start at n equals 0. So we know that we have an x to the n term, and then the coefficients. Well, each one of those coefficients is 1 less than a power of 2. So this is 2 to the first minus 1. This is 2 to the second minus 1. So since we're starting at n equals 0, we can write 2 to the n plus 1 and then minus 1. I'll rewrite it down here so you can read it. And then we'll check to see if it actually works. So 2 to the n plus 1 minus 1 times x to the n. When n is 0, we have 2 to the first minus 1 times x to the 0, or 1 times 1, which is 1. When n is 1, We have 2 to the second, which is 4. 4 minus 1 is 3. And x to the first. Okay, one more. When n is 2, 2 plus 1 is 3. 2 to the third is 8. 8 minus 1 is 7. And x to the second. So did that work out? Okay, the next page. Evaluate the integral of x over 1 minus x to the 8th dx as a power series. So how should we start this one? Note the integrand is x over 1 minus x to the 8th, which is the same as x times 1 over 1 minus x to the 8th. So if we first begin by finding a power series representation for 1 over 1 minus x to the 8th, just using the geometric sum formula, then 1 over 1 minus x to the 8th is 1 plus x to the 8th to the first plus x to the 8th to the second, and so on, plus x to the 8th to the third. If we expand those, we get 1 plus x to the 8th plus x to the 16th plus x to the 24th, and so on. Okay, then x over 1 minus x to the 8th. As a power series, we just multiply the power series by x, and we get x plus x to the 9th plus x to the 17th plus x to the 25th. The next one is x to the 33, and then x to the 41st, and so on. So at this stage, each of the exponents is just a multiple of 8 plus 1. So 8 times 0 plus 1, 8 times 1 plus 1 is 9, 8 times 2 plus 1 is 17, and so on. Okay, now we can compute the integral and write it as a power series. So we put the integral, or the constant of integration c, and then we write down the antiderivatives of the terms, term by term. So c plus x to the second over 2 plus x to the 10th over 10 plus x to the 18th over 18, and so on. Okay, so there it is. Let's take a stab at the sigma notation. Okay, so the exponents are multiples of 8 plus 2. So we can start at n equals 0. and then write these as x to the 8n plus 2 divided by 8n plus 2. So that looks like that's the right formula. And the next exercise, find a power series representation for the natural log of 1 plus x. So this looks familiar. We've done this before, I think. So what's the strategy for finding a power series representation for the natural log of 1 plus x? Yeah, let's take the derivative of f. The derivative of the natural log of 1 plus x is 1 over 1 plus x. And we know how to find a power series representation for 1 over 1 plus x. Think of this as 1 over 1 minus negative x. And then the power series representation is 1 plus the term negative x to the first plus the term negative x to the second plus the term negative x to the third, and so on. Okay, so this is 1 minus x plus x squared minus x to the third plus x to the fourth, and so on. In sigma notation, this is an alternating series. So negative 1 to the n and multiplied by x to the n. Okay, so that means the natural log of 1 plus x since 1 over 1 plus x is the derivative of the natural log of 1 plus x, the natural log of 1 plus x involves the integral of 1 over 1 plus x. So we'll put down c for the constant of integration and then write down the antiderivatives term by term. So we get c plus x minus x to the second over 2 plus x to the third over 3 minus x to the fourth over 4, and so on. So we'll write the natural log of 1 plus x equals c plus the series using sigma. We can start this one at n equals 1. It's an alternating series, so negative 1 to the n minus 1, and then times x to the n over n. Yeah, I think that works. To find the constant of integration c, when x is 0, the natural log of 1 plus 0 equals c plus 0, because all of the terms in the series have x, but the natural log of 1 is 0, so this means the value of c is 0. So we can write the natural log of 1 plus x explicitly as the power function from n equals 1 to infinity of -1 to the n minus 1 times x to the n over n. All right, on the next page, we're going to borrow what we found on this one. This one says evaluate the integral of x squared times the natural log of 1 plus x as a power series. So we'll rewrite what we have for the natural log of 1 plus x that we just found. So in expanded form, this is x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4, and so on. Then we multiply both sides by x squared times the natural log of 1 plus x is x to the third minus x to the fourth over 2 plus x to the fifth over 3 minus x to the sixth over 4 plus x to the seventh over 5, and so on. And then evaluate the integral of x squared times the natural log of 1 plus x dx. So term by term, we just write down the antiderivatives from the series above, and we get x to the fourth over 4 minus x to the fifth over 10, and then plus x to the sixth over 18, and so on, x to the seventh over 28. Hey, why don't we see if we can write down the sigma notation for this. Well, when we started the first term, x to the fourth, all of the exponents increase by 1. The denominators increase by first by 6, then by 8, then by 10. So I'll let you work on that. Let's look at the next example. Find an infinite series that is equal to the natural log of 2. So any ideas on how to find an infinite series that's equal to the natural log of 2? Any ideas? Well, there's something on this page that we can use. I'll give you a few more seconds. Okay, at the very top, we have the natural log of 1 plus x, a power series for that. So the natural log of 2 can be found if we just replace x with 1 on that. Okay, I'll rewrite that since can't see everything at once. So the natural log of 1 plus x is x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4, so on. So the natural log of 2, using this function, this is just the natural log of 1 plus 1, replace x with 1. We get 1 minus 1/2 plus 1/3 minus 1/4, and so on. So the natural log of 2 is equal to the infinite series. It's alternating. We can start at n equals 1. The first term is positive. And the terms have the form 1 over n. Okay, we have a name for this series. What do we call that? It's the alternating harmonic series. Alternating harmonic series. So a few days ago, we showed that the alternating harmonic series converges, whereas the harmonic series diverges. And the alternating harmonic series converges to the natural log of 2. So you might remember in algebra, the natural log of 2 was a number that came up pretty frequently in algebra. So the decimal approximation for the natural log of 2 is 0.6931471806, and so on. All right, let's go up here and see if we can figure out a formula for this series. So let's see, if we start at n equals 1, Then in the denominator, we have n times n plus 3. And in the numerator, we have x to the n plus 3, I think. So we can test it. When n is 1, the numerator is x to the 4th, and the denominator is 1 times 4, or 4. Oh, it's alternating also. We'll throw that in a second. When n is 2, we have 2 times 5, which is 10, and x to the 2 plus 3 is 5. Okay, that works, and then multiply this by negative n to the n minus 1. Okay, we're out of time. Go ahead and sign in for attendance.
I might miss this Friday.
You talk.
Yeah, I might miss this Friday too. We have a meeting in Logan.
Oh,
I don't know yet.
Oh.
I don't know what time we're leaving.
Okay.
Would I be able to?
That's the test.
Would I be able to take it like Thursday if I needed to?
Yeah. Just let me know as soon as you know.
Okay, sounds good. Thank you.